All right, good morning, everyone. Welcome to the session. Thank you for taking time to come out and attend this particular session. My name is Jatin, and I'm AWS Partner Solutions Architect. And in my role, I work very closely with SI and ISV partners to do technical and business enablement, primarily in the AWS database services space. Now, last year when I was in the Global Partner Summit or in reInvent, I did talk about database migrations and how to accelerate migrations from the enterprise databases to Aurora PostgreSQL. But this year when I was working with my partners, one of the bigger feedback which I received was they are doing a lot of proof of concepts and they're building operational runbooks with the customers. So if they can learn a few things about Amazon Aurora with a perspective that how to run it better in operations and how to gear up their learning process so that they can be more operationally ready, that would be really great. So that's what I'm going to do in this session. We are going to take a look at Amazon Aurora from an architectural standpoint and then take a look at various features and how you can exploit those features to best suit in your operational environment and learn something about deploying it out of the box and things which you have to change on top of Amazon Aurora out of the box configuration so that you can wisely use that configuration in your operations environment, right? All right, so before we go there, I just want to discuss quickly what the current overall broader RDS portfolio looks like. Now, if you look at the RDS portfolio, what we offer to you today is 7 different engines. I'm counting Aurora twice because it offers both MySQL and PostgreSQL flavors. Apart from that, we offer you 2 enterprise engines, Oracle and SQL Server, and we give you 3 open source engines, MariaDB, PostgreSQL, and MySQL. Now, this sometimes causes a confusion as people tend to think that Amazon Aurora is not part of the RDS portfolio, which is actually not the case. Amazon Aurora just has been branded especially because it has been engineered and built ground up to be cloud native. But it's very much a part of the RDS portfolio and in fact uses the same management platform as the rest of these managed RDS or EBS-backed RDS engines use. Now people on the field, you will normally hear people talking about these 5 engines, Oracle, SQL Server, and rest of the 3 open source engines as EBS-backed RDS engines or managed RDS engines. So you'll keep hearing these terms back and forth, but just keep in mind that Amazon Aurora is also part of RDS and offers you all these capabilities which the rest of the RDS engines do. But since it is engineered in a different way, things are done in a little bit different fashion in Amazon Aurora. Now, talking about Amazon Aurora and how it's different, Amazon Aurora, when it was being designed, the big idea was that if you have to design the platform today, keeping in mind how the RDBMS engine would like to use that platform, keeping in mind the RDBMS engine, how would you design it today, keeping the cloud thing in mind, right? Keeping the microservice design in mind. And that's how we actually designed Amazon Aurora from ground up. But one thing which really stands out in this architecture is how the storage was designed. The Amazon Aurora storage, as you might understand, is a log-based storage and really understands the database redo log changes which are happening in the database and can consume those changes directly into the storage subsystem without having the need of doing full page writes. In doing so, we came out with a highly available, durable, and fault-tolerant storage. And if you visualize that, this is how it actually looks like from an architectural standpoint. So if you provision Amazon Aurora cluster today, this is how you will get the storage volume laid out. One thing which stands out is this storage volume is spanning 3 different availability zones, as you can see, and is powered by hundreds of storage nodes. So what we do is when you spin up a cluster, we take 10 gig segments which contain your data and we right shard them across 3 different availability zones and 6 different copies. So these color codes which you see, the red, orange, and yellow, these are copies of your data residing in 3 different availability zones. So what it gives you is a very highly available architecture, right? So if your AZ goes out, you still have other 2 AZs serving your data. A very, very highly durable architecture because we are making sure we are writing 6 different copies. But what we do is actually wait for only acknowledgement from 4 out of those 6 copies to give you an acknowledgement back so that those are durably written down. And in doing so, what we do is to make it performant, since it's a log-based storage, we don't do full page writes, right? And also we do not rely on very heavy voting consensus protocol. So we don't wait that each of these copies will vote and come back. But what we do is, as the transaction is being written down, we are just writing it down to the storage subsystem, and later we order that bit based on LSN, right? Net, what you get is a very highly performant volume, which if you compare to stock PostgreSQL is giving you 2 to 3x more throughput, right? But literally thinking about end user perspective, it's really a very simpleton storage system which grows up to 64 terabyte. That's something which you have to just keep in mind. So all these engineering marvel things which we have done to make it performant, from an end user perspective, it's really a very simple interface which is given to you. All you have to keep in mind is that it's a self-healing storage, it's highly available, and it grows up to 64 terabyte without you having to do anything, right? Another thing which you have to keep in mind is we also offer you 15 different read replicas, all of which are connected to the same underlying storage. So you can take advantage of that architecture. Now, keeping this architecture in mind, what are those things which you can take as a learning when you are doing POCs or when you are doing your operational runbooks? So let's put our operational hats on and start looking at those topics, all right? The first one I want to discuss with you is the high availability, how we achieve high availability in Amazon Aurora, and how it compares with the EBS-backed RDS engine, right? And what's the multi-AZ concept in Aurora, and why do people get confused sometimes? So this is the EBS-backed RDS engines. Remember the 5 engines which I showed you. So if you think about how high availability is achieved with the EBS-backed RDS engine, this is how the steady state would look like. So if you go to Amazon console and choose multi-AZ in RDS, this is how the steady state will be. Your application is connecting using an endpoint, and you just see only one DNS endpoint which is connecting to your database in RDS multi-AZ, right? You do not see the other secondary side. But behind the scene, what we are doing is we are doing a storage level physical replication, and we are provisioning a passive side for you, which is acting as a high availability instance, right? So from a user perspective, what happens is if their primary side goes down, the automation kicks in and decides to do a failover, in which case we simply flip the roles. The secondary assumes the primary role, and we try to recover the secondary for you. This typically lasts for 1 to 2 minutes. It's a DNS-based failover, so we put a new DNS entry in there, and the failover happens, right? If you have to provision a read replica in case of RDS, what you do is you just go to console and create a separate read replica. The secondary instance does not act as a read replica. It is just staying there to act as a high availability passive failover instance, right? So this is what basically happens when you provision a read replica, and you can direct your read traffic in there. Remember that read replica in RDS, EBS-backed RDS or managed RDS is not used as a failover target, but you can write automation on top of that to actually use that as a failover target. But from a RDS perspective, we do not provide that as a failover target. The point I'm trying to make here is the failover, high availability, and read replica are very clearly defined concepts in a managed RDS. But if you compare that with Aurora, and you go to console and provision an Aurora cluster, what you will get is just one instance which is connected to a multi-AZ storage, right? Remember that I said if you do not select a multi-AZ option, this is how you will get it. But the storage subsystem here is actually multi-AZ. It's spanning out 3 different availability zones. So what happens with this is if the primary instance goes down, it goes bad, we will just try to recover that instance back. It can come back up in the same availability zone, or it can come back in a different availability zone. You will see some outage, and your application will just reconnect here. But if you go to AWS console and click the multi-AZ option, what we will give to you is another replica instance, which acts as a failover instance. Now, see the difference here. We call it the read replica instance, but that read replica instance actually acts as a failover instance. So it's not like the managed RDS engine where the failover instance is a passive instance and does not act as a read replica. So people just sometimes get confused that I do not have an application which can redirect my read to the read replica. So I do not need a read replica instance. So let me just not provision a read replica instance because it is just a highly available system, right? Because the storage is already highly available. So why do I even need to have a multi-AZ configuration and the second instance which is idle when I'm not using that for a read replica traffic? Just remember that if you are trying to have a high availability, the best design is to choose a multi-AZ which will provision a read replica which actually acts as a failover target. So in this case, what happens if your primary goes down, we simply nominate the read replica instance as the primary and a DNS failover happens, and that just assumes the primary role. Much faster, takes like 30 to 40 seconds of time. Now on top of that, of course, you can have other read replicas which can also act as failover target. It's not that other read replicas do not act as a failover target. So any read replica in Aurora cluster can act as a failover target. But you can set priorities and say, this is the one which I want to be of higher preference, and the failover, if it happens, should happen on the larger instance first and then the smaller instance. As a good practice, as a good design practice, the thing is you should always have one replica instance which is similar size to primary and set it to the highest failover priority. We call it tier 0 priority, and try to use that as a failover target. If that failover does not happen there, then the other read replica can take as the role of the failover instance as well. So key takeaways. First thing, understand durability versus availability, what we are providing to you at the storage level versus at the instance level. And if you want to design for higher availability, use the read replica, which is also the failover instance to your advantage. Second point, Aurora storage is always multi-AZ. Keep that in mind. Some partners and some customers, they come back saying that I did not select a multi-AZ option, but still it's a multi-AZ system that is being given to you. It especially comes handy when you are doing performance baselining against your on-premises system. What people do is they'll select a standalone system, they'll run a database there and run their performance benchmark against it. I've seen people, they run like EC2 with directly attached storages and run SQL Server or Oracle on it and get certain performance numbers and try to compare that with Amazon Aurora when doing POCs. Remember this thing that this is a highly available and durable system. You cannot turn off multi-AZ at storage level, right? We are writing 6 different copies synchronously. So when you are doing these POCs, keep in mind that your representative on-premises system against which you are benchmarking, configure that in high availability mode, in sync write mode, and then take performance numbers from there and try to compare it against multi-AZ system or non-multi-AZ system. All right, very important concepts when you are doing your POCs. Next thing, let's look at the endpoint naming, how the failover priority work, and cluster cache management, just to round up our high availability discussion. So let's revisit that architecture. Now, out of the box, what we provide to you is a cluster writer endpoint, which always and always follows the primary, which will always follow the primary. It's guaranteed. So when the failover happens, we point it to the new primary instance. Only after the DNS failover has completed, it is guaranteed to point that to your primary instance. So we always encourage that whenever you are working with your application, do not use the instance endpoint. Work with the cluster endpoint because it follows that instance, right? But to achieve higher availability, what you can also do is maintain a list of instances in a file and then populate your host string based on those list of instances. What you would have to do in that case is you would have to look up the instance and you have to write that logic in your application that when you connect your application to Amazon Aurora, because with the list of instances, you can even connect to a reader instance, right? So when you connect there, you go there and ask, hey, what's your current role? If it's reader, which one is the current writer instance, which one is the primary, and is it the stale data or not? If it's the stale data, you wait for some time and just recheck that. And based on that, you can get and connect very quickly to the new primary after the failover, right? So this is something which you would have to either use smart drivers or design on your own to if you want to achieve even a high availability. But if you want to keep it simple, always use the cluster writer endpoint, which is guaranteed to use the DNS thing to point to the primary instance. Another thing people which often forget is these failovers are all based on DNS, right? So if say your application has a tendency to cache the IP address, you would have to do what you have to do on the application side to realize that failover in a faster way. For example, you would have to set aggressive TTL timeouts, or you have to work with TCP keep alive, so your sessions are not simply waiting for the TCP timeout settings to realize that the failover has happened and the role has changed. So you have to work with those settings to realize a faster failover configuration while working with Amazon Aurora. Another thing is, you saw that as I provisioned the read replica, the cluster reader endpoint now points and round robins the connection to all the read replicas. Now, this is an important concept as well. You see that if you provision new read replicas, it's not that the existing connections will immediately respawn to the new read replicas. You would have to cycle those connections. Only the new connections will start going to the new read replicas as you keep adding them to the cluster. So keep that thing in mind. Some people think that since they have provisioned 5 more read replicas, all their existing connections should just automatically go away there. But you would have to do things to cycle those connections so that those connections actually go to or start going to the read replica side. Only the new connections will go there. The existing connections will still stay on the older wherever they were established, right? Another important concept here is that we are simply doing a round robin and handing off the connections. So if you have a requirement where you feel that there are some read replicas which are larger in size and serve a particular kind of traffic, and you need to address that kind of need, you should be using what is called a custom endpoint. A very powerful concept again. So think about it. If you have an application where you are always hitting, say, 5 tables or 6 tables, and you want to take advantage of the caching, right? So with custom endpoints, what you can do is just use one custom endpoint to point to 2 read replicas which are smaller in size and serve only those 5 tables. And then you can have another cluster or a custom endpoint to point to one larger one where you are running your larger reports and so on. In this diagram, I'm not showing that custom endpoint is connected to primary, but you can also design the custom endpoint to connect to your primary instance as well and take advantage of that concept. People generally tend to use just cluster endpoint and forget about that there is a custom endpoint as well, which they can use to their advantage. Another thing which I have noticed is more of a nuisance is that when you provision a cluster, say you named it PRD HRMS, the way we name our instance out of the box is PRD HRMS instance 1, and the read replica instance will be named PRD HRMS instance 1 hyphen, we will append the availability zone name in front of it. So US East 1D or something like that, right? What people sometimes do is they'll name their instance, they'll say, I don't like this name, let me name it primary because this is my primary instance. Notice that how the read replica instance is also named PRD HRMS primary hyphen US East 1D. So it's a very meaningless configuration. Just wanted to point it out because a lot of people make that mistake because the roles can change at any time and it just follows the naming convention that you have done on the primary instance side. So it's a very meaningless thing to do. Best practice is to use either node 1, node 2, node 3 or some meaningful names which can actually benefit you. Primary and failovers generally don't. Just to round up our discussion, you can also take advantage of a feature which we came out with Aurora PostgreSQL was cluster cache management, right? Now, if you look at this, this represents how the application performance is after a failover has happened. And one of the database engineers actually ran this performance benchmark where he was running 350K transactions. And when the failover happened, it happened in 32 seconds. And the application performance, but if you notice the application performance here, it did not come back to the same level until a long amount of time was spent, which was around 340 seconds. So even though the failover had happened, the cache was not warmed up to start serving the traffic in the same way, in the same performant way, because the database cache was not warmed up like that, right? So to help with that feature, we came out with cluster cache management. Basically what happens with that is that in this case, the reader instance, and you have to nominate that reader instance actually to enable this feature. So you have to choose an instance. As a good practice, you would choose an instance to be the same size as primary. You will set the failover priority to 0 on both the primary and that failover instance, designated instance, which is the highest priority. And you would set APG CCM enabled on, which is a cluster parameter. Once you do that, this failover instance, this particular instance, will start sending the image of its cache to the primary. And what primary will do is see what blocks it wants that failover instance to load so that it's a good representative of the primary's cache. And it will start sending those block addresses back to the read-only instance. Remember that we are doing some additional work once you enable that. But as a net benefit, you will see that once the failover happens and we repeated the same performance benchmarks, the TP90 performance or the application performance came back pretty quickly. as compared to the previous overlapping one. So again, very powerful feature. Just keep that in your back pocket when doing your POCs and designing for operations. So key takeaways from first two sections: understand the failover priorities, design according to that. A good practice is design at least one read replica instance, same size as primary. Effectively, you would want to keep the same database parameters on that instance. Endpoint usage, understand how the cluster endpoint behaves and how you can take advantage to achieve higher high availability, and understand how the naming works. And another important concept is that understand the read and write work in tandem. We have the same underlying storage. It's not that the reader is connected to a separate database instance. So you have to be careful of the fact that what kind of workload you are running on the read replica. It works in tandem with the writer instance. For example, if you go ahead and say truncate a table on the primary instance, of course your queries on the read replica will be affected with that, right? So just keep that in mind. Now moving on, let's see what are the caching changes we did with Amazon Aurora, and understanding those caching changes, what you can do when building your POCs, and what are the parameters you should keep in mind, right? Now in this diagram, I'm just comparing how the PostgreSQL works, native PostgreSQL, versus how Aurora works with respect to their memory configurations. Now if you look at this, represents just the memory. So if you provision PostgreSQL out of the box, it will consume roughly 25% is reserved for the PostgreSQL processes and the OS processes, and shows up as the freeable memory in there. 25% is the default for the shared buffer, which is consumed by PostgreSQL, and rest 50% is taken by the Linux page cache. Now if you select a data in native PostgreSQL, what will happen is it will try to read that data from the shared buffers. If it's not present in the shared buffers, it will take advantage of the Linux page cache. If the data or the block is not present there, it will go ahead and read it from the storage. This is how basically the logical I/O and the physical I/O concept works, right, with databases. But what happens in this case is that since you are having these duplicate buffer in terms of Linux page cache, you are ending up wasting a lot of space. So on a typical 488 gig RAM system, which is like a 16XL server, you are effectively getting 240 gig in the cache. So thus effectively wasting quite a bit of RAM. Comparatively, in Aurora PostgreSQL, the default for shared buffer we chose was 75%, because we do not rely on the Linux page cache to do write-aheads because of the optimizations which we built. As an effect, when you read the data, we simply look at the shared buffers. If it's not there, we just simply read it from the Aurora storage, and effectively giving you a larger buffer cache and better performance. But every design has pros and cons. The advantage with PostgreSQL, what they get is that if the PG and the OS process die, they still have, with the PG and OS process, when it dies, the shared buffer will also go away, right? Because that will die as well. So in this case, you do not face the cold start problem. The buffer cache will still be able to rely on the Linux page cache, which will have the buffer images because it's duplicate buffer, and you are in a happy state. But we do not have that in Aurora PostgreSQL. So effectively what we did in design was that we came out with the concept of survivable cache, and we split the dependency of shared buffer out of the PG processes, so that if the PG process dies, the shared buffer still survives, and we are in a happy state as well, right? So this was the change which was done with Aurora PostgreSQL. Now from an operations standpoint and the POC standpoint, you need to just understand that. But what do you need to do, right? What do you do about it? Is there anything which you need to do? Yes. Okay, what is it? So think about your workload. If you are running a workload, there will be components in your workload which will depend on the freeable memory, which will depend on the Linux freeable memory. Now, since we have consumed 75% as a default in Aurora PostgreSQL, the amount of memory which will be left will be lesser than as if you compare it with the shared buffer configuration in the native PostgreSQL, where we were just allocating 25%. So if you are in a position where your workload requires, say, very high auto vacuuming processes running, say you want to up your auto vacuum max worker. Now auto vacuum max worker, say you have a lot of small tables which you want to auto vacuum. You have to work in tandem with the maintenance work mem. So the amount of freeable memory which will be used is maintenance work mem times auto vacuum max worker processes and so on, right? Another thing is if you are doing a lot of parallel queries and you are running sort and hashes, Work mem configuration, generally it's like quite misunderstood configuration and people just up that configuration, I have seen. But if you are actually using that kind of mechanism, again, you will tend to use a lot of freeable memory which is available on the box to utilize that. So look at your workload effectively to see you have enough freeable memory available to effectively work with your workload. Now I've given one example here. For example, in a R5 large, if you see, you will see that you have 16 gig RAM, and by default we are allocating shared buffer to 9 gig. Now we started with 75%, which was leaving 1 gig earlier, but we changed it recently for a smaller box. And now this is the default configuration which is available. Now this would keep changing, right, as we learn more and more from platform, but you keep this thing in mind that when you are taking the default configuration, we always recommend that trust the defaults. The defaults have been designed, the database parameters have been designed to work with most of the workload effectively for this platform. But your mileage may vary, your workload may vary. So always test your workload against the given parameter and the given configuration. So in this case, if you have a need that you are building large indexes, or you are doing a sort operation, hash operations, and those kind of things where you need to rely on the Linux freeable memory, you might need to think of either choosing a larger box or working with these parameters to tween and tweak them so you don't run into out of memory issues while running it in operations. Very effective thing you should always keep in mind when designing your operational things, right? Next, since we are already talking about the database parameters and cluster parameters, let's talk about how they actually work and what are the things which you should know, right? Now with Amazon Aurora, we have concept of cluster parameter group and database parameter group. The reason they are different is that there are settings which we want you to apply on the cluster level parameter, on the cluster level, right? So the cluster parameter group is basically a container for those settings which are to be applied at the cluster wide, and database parameter groups are those settings which are applied at the instance wide. And you can have different instances carrying different instance parameters and so on. So if you think about it, anything which affects the whole cluster or the shared storage because it's shared across the cluster will sit in the cluster parameter group. So things like if you are forcing a SSL connection on the server side for PostgreSQL will sit in the cluster parameter group. Things like enabling extensions can be done at the cluster level. And things like setting connection settings and work memory can be done at the instance level. So understand those differences, right? Also understand that out of the box we give you default parameter group which you cannot change. So the step one when you will just configure a cluster out of the box is always create a custom parameter group with a copy of the default parameters which you can actually build your practice on and on which you can make changes as well, right? Another important thing is always baseline on the default parameters so you have a good robust baseline to work against. Now, another thing I wanted to show you here is what are some of the few things which you can learn more about database and cluster parameter groups. Now, one thing is, and I've already talked about it, that the PostgreSQL defaults and the Aurora platform defaults are two different things, especially if you are coming out of PostgreSQL background. You're not doing a heterogeneous migration, say you are doing a homogeneous migration, but you're used to working with a PostgreSQL defaults, right? So you would notice that PostgreSQL defaults and Aurora defaults work in two different ways. Now, we took the example of shared buffers, but we did several other enhancements to make PostgreSQL work best with Aurora platform. So for example, we did a lot of enhancements on vacuuming parameters. So because the storage is fast enough, vacuuming also works aggressively and works really fast. We will talk about auto vacuuming changes, but just keep in mind that, for example, these vacuum scale factor and analyze scale factors will work differently on Amazon Aurora platform. So just keep that in mind that our defaults are designed for the platform, and it's recommended practice that when you are running a proof of concept, always take a baseline against the default, trust the default, because whenever you will come back and work with us with either AWS premium support or work with our service team, they'll always come back and say, hey, what's your performance against the defaults which are known to work with most of the workloads? You are free to tune the parameters, but always take a good baseline with the default parameters and then understand the differences and then try and tune on top of it. Another thing to remember is that there are some parameters which you won't be able to change. Now, a lot of people, if they're coming from PostgreSQL background, would be familiar with hot standby feedback. It's used on standby for query conflicts and how the vacuuming should behave. to not clean up the rows because the queries are still running there. Some of those parameters won't work on Aurora platform because of the way shared storage structure is and the way the read replica is pointing to the same underlying storage. So just a thing to keep in mind when you're building your operational runbooks on what to change and what not to try to change. Another thing is that, and people often ignore this fact, that there are read replica parameters at instance level which you are free to change. And we encourage that whenever you are working with, say, a reader traffic or your workload which is just getting answered from your read replica, look at the parameters which affect your reader traffic and design your parameters accordingly. Now, as a good design practice, you would always want to have one failover instance in Amazon Aurora which has the highest priority, and you would set the parameters on that instance same as your primary instance, because after the failover you do not want to be surprised by seeing that the parameters have changed because there were different parameters set, right? So you would have one instance which is like sized as primary and set the same parameters in there. But there are other read replica instances as well. So for example, you may not want to set very high maintenance work mem on those read replica instances and take advantage of more shared buffer available out of the box for serving your read replicas or reader traffic from there. So just some things to keep in mind when working with testing and POCs and operations. Now another thing, an important one, is how do you run maintenance operations, right? Now people often, when they are adopting this solution, they look at migration runbooks, how to migrate the data, how to do performance testing, and so on. But we always encourage that you think ahead and think about how you will build your operational runbooks to be successful in maintenance operations and in actually achieving operational excellence while running in operations. So the first thing I want you to understand is how the version management works with Aurora. Now, when we released Aurora version 1 in Aurora PostgreSQL, the major version which we supported was 9.6. Now, PostgreSQL changed its major versioning scheme. They earlier used 9.5 and 9.6 as the major version, but now they call version 10 as the major, version 11 as the major, and so on. You can see version 2 maps to Aurora major version 10, and we recently released support for major version 11, which is Aurora version 3, and so on. Now, the thing to remember is we closely follow PostgreSQL community for all the bug and the patch fixes and so on. We try to always follow them as closely as possible, especially if there is a security bug which is released or if there is a CVE impacting Amazon Aurora. The service team really scrambles to get that CVE or bug or patch fix out ASAP out for you to support. Just take a note of the patching versioning scheme. A good point is to read the release note to understand what those patch releases are coming out and how they affect your system. Now, three main things you have to understand here is, one thing is when running operations, you would need to think about major version upgrades. Right now with Amazon Aurora for PostgreSQL, we do not have the support for in-place major version upgrade, but it's in the roadmap and should be out pretty soon. Whenever that is done, we will release support for version 9 to 10 in place, 10 to 11 and 11 to 12 whenever it is out. Major version upgrades are generally affecting the system catalog tables and should be rigorously tested. Those are major changes. So a good practice is that you plan ahead and actually do that in your QA and test environment and see the application performance for yourself. Minor version upgrades comparatively are binary swap and lightweight in mechanism. One thing which we recommend is always turn on auto minor version upgrade on so that we can actually take advantage of the maintenance window which you have defined and automatically push the minor version upgrades. Now, not every minor version upgrade will be applied if you have chosen auto minor version upgrade, but only those minor version which we have marked as the preferred minor version, minimum minor version, those will be applied whenever you have chosen the auto minor version upgrade in the maintenance window, right? Another thing is there are patches which we keep on releases, security and bug fixes. Please go ahead and apply them. Those are important as well. One example is that we have recently pushed out a new SSL certificate version which has the date for March 5th. Right now, if you go into Amazon console and see, you will see that there is a notification which sits like this. So go and take a look at those notifications. Always test that. In this case, like, it will recycle You have to test your applications that it works against new patch releases and so on. One thing people just get confused is when the patch is released, all the new servers, new launches are actually released on the highest patch set level, but your existing servers won't be automatically pushed to the highest patch set level. You have to go ahead and apply those maintenances yourself. Some of those are mandatory and will be pushed out with notifications like this, but some of them will just sit in your notification window and you have to actually select those patches and apply them. Right? So there is a little bit difference between how we handle auto minor version upgrade with respect to applying the minor version versus how we apply the patches. Now talking about maintenance operations, it's not just major and minor version upgrade and how the server versions work and so on. You tend to go with the application maintenance as well, right? You release DDL changes, you create indexes, you create application versions which are recreating tables, and there are whole lot of maintenance operations which go on. One important concept which I generally tell people is understand that we talk a lot about distributed log-based storage, which is highly available in architecture, but there is actually a local storage as well, which is attached to your EC2 instance or your writer instance and reader instances as well, right? Now that local storage is limited in size. Typically it's 2x the RAM if you see as of today. But what that local storage is used is to store your log and temp files. So one common mistake people do is they just turn on aggressive logging and it just sits there and consumes the space from that local storage. Now if you're trying to run heavy maintenance operations, you might run into space issues with temp files and the error might look like this. People don't generally understand this out of the box because they're thinking the storage might grow up to 64 terabyte. Why index create is leading me into this kind of problem. So if you are running aggregations and sorts and those kind of operations, keep in mind that we will first use a maintenance work mem. You can try to upsize that and do it in memory. But then you have to look at the size of this local disk as well. The good practice is to identify those kind of things which are leading into these errors. I use the CloudWatch matrix related to free local storage to watch that local storage. It is out in the public documentation, and I'll show that to you in a while as well, how you can build alarm on top of that to watch the free local storage. And then try to tune your workload to actually use the in-memory sorts and things like that and avoid disk spillage. Very important concept. People realize it later if they are just starting with Amazon Aurora, that they need to work with this as well. Another thing while we are talking about maintenance operation, and a very powerful concept which is out there is cloning. Now, cloning when it came out, a lot of people understood it as a way to run their ETL processes or run their QA and testing as well, right? So I'll first explain the concept of cloning, and then I'll explain how you can use it for your maintenance operation as well. So when you create a clone, and say you have a reporting application where you want to run a giant report, what we do is when you create a clone, it's actually a separate Aurora cluster, but that cluster does not come with its own storage volume. When you just go to Amazon Aurora console where you have a cluster already running and you say, I want a clone, we just provision an instance, but we create a clone storage, which is actually a virtual storage. It's not the full copy of the production instance. But instead, what we do is we just create pointers to your primary storage in that case, right? So if you are reading from that clone system, which is altogether a separate Aurora cluster, what we are doing is instead of reading from or writing that data to the clone storage, we will just create that pointer and read from your primary storage as a reference copy. But when you just try to write the data in the clone storage on the data which has already been referenceable from the primary, we do what we call copy on write. So you see the advantage here. When you create a clone, you are not paying for that shared storage system. You are just paying for the instance which you have created, but you are getting all your data as is of the point in time when you have created a clone. Now, if you add more data to the clone, because say you are creating a new table or creating a new index on that clone environment and you want to test against it, or you are running your ETL on top of it, which creates 10 more tables, we will just write to the cloned copy and we won't touch the primary storage here. But if you are writing to the primary storage, similarly the primary does not impact the cloned storage and the data will just be written to primary. So these are in fact two separate clusters and behave very independently to each other. Only the references at the point when it was created are pointed to the primary storage. But if you go ahead and change the old block on the primary, we just do a copy there, and you pay for whatever are the changed blocks on the cloned storage. Now, a very powerful concept. People generally understand it for ETL and reporting system, but since we are talking about application maintenances, I highly recommend that you keep that in your operational runbooks when you are designing your POCs or building your operational runbooks, that whenever you are releasing a new change, say index creation or creating a few tables, and you want to test your applications, you can simply just go ahead and create a clone, which is like a prod-like copy. Test your changes there. If you like the change, just confidently roll that out to your production system, right? All right, now talking about operational and POCs, I don't think the discussion will complete if we skip the security subject. So I'll just go over some concepts which are available for Amazon Aurora, and then I'll also talk how you can use it to your advantage and some things which were released in last year and how people actually use that, right? Amazon Aurora, as we say, is secure by default. We offer you VPC and recommend that you use private subnets if you are working with Amazon Aurora, or if you are working with AWS environment in general. Most of you would be familiar with VPC concept, right? Generally, when working with these POCs, a recommendation is that you always work with your network and security guys in your team to actually do the network and security hardening. I highly encourage practices that don't leave that discussion for the time when you will go into operations to figure that out, right? When you are launching your complete stack, your application, your Lambda functions, and whatnot with the database environment, make sure one thing that the production environment is actually launched in a private subnet and everything is tested accordingly. That hardening exercise should be taken as job 0, or like the security job should be taken at the highest priority, right? So this is a pretty known concept. You can take advantage of direct connect and VPN connections, but nonetheless that you should take it lightly. So just keeping it in there. Now talking about security, people also talk about encryption. For encryption at rest, we offer you integration with KMS, which uses envelope encryption, which is a 2-level encryption. We have a master key, which actually encrypts your data key. The data key is in turn used to encrypt your data, right? Now, one of the things which people ask me about encryption is about performance overhead, and I tell them that we do it at the storage level. So I can't even think of a case, why would you turn it off, right? Now, you should really think hard about it when you're doing your POCs or getting operationally ready. If there is no performance impact and you're not paying separately for it, why would you disable encryption? Like, I really encourage you to enable encryption at rest and take advantage of it. One thing people think is that if I'm encrypting my data, it's very tough for me to decrypt it if I later need to share it. Of course, it's hard to decrypt. You need the keys to decrypt it, right? Otherwise, what's the point of encryption? But one thing is, if you're sharing an encrypted snapshot across the accounts, what you can do is you can create a copy of your snapshot, and at the time of copy, we give you a flexibility to choose different keys. And when you're sharing that encrypted snapshot with across account or send it across region for whatever use case you might have, you can also send those different keys. So you're not sharing your original data keys, which you have used to encrypt your snapshot, but you are actually creating a new key and re-encrypting that snapshot, and you can easily share that. So I can't really think of a operational scenario where you would want to disable encryption, right? So highly recommended to enable encryption. Now this was encryption at rest. For encryption at transit, we offer you SSL. Now RDS on server, Aurora on server keeps a SSL certificate. The thing which I showed you in pending maintenance, if you paid attention, was that we are rotating that certificate now after a couple of years. But you can take advantage of that. To enforce SSL, you use 2 different settings. One is on the server side and one is on the client side. Now this is very typical to PostgreSQL, nothing to do actually with the Aurora platform, but just to cover that, on the client side, you can set different settings. We recommend do not use disable and allow, which will allow the plain text communication between the client and the server. Go with at least the default setting of prefer, but highly encouraged go with the require setting, which will enforce SSL and will drop any non-SSL connections, right? You can use verify CA and verify full as well. which actually does the authentication on the host side as well, that you are actually talking to the intended host and are not actually going into man-in-the-middle attack kind of thing, right? A couple of people have asked me like what SSL versions we support. Do we support TLS 1.2 and so on? You can test it for yourself by using SSLize command, which will give you a very clean output, and you can use it to your advantage. Another thing, and I really wanted to talk about this because Secrets Manager got launched just last year. Before that, we had two different ways of authentication. We use the database password level authentication, which PostgreSQL by default uses MD5 and SALT to use database level authentication, typical user ID and password level authentication, right? Apart from that, we came out with IAM, which you can use to have a token-based access, and we use STS actually to generate a token which is valid for 15 minutes. And in that case, PostgreSQL actually relies on IAM to do the authentication on your behalf. But what we really came out with last year was the Secrets Manager and integrates with RDS environment. So think of it as, say, a DBA sets the password for your application. The application is connecting with some username and password. Your DBA sets the password, but there is always a fear that DBA knows the password, right? And then I have to rotate the password, and when I rotate the password, I have to do it carefully as well. I have to do it in the maintenance window and so on. With Secrets Manager, we store those passwords, user ID and password for you, and we rotate them for you as well, and we integrate that with IAM, so you can take advantage of IAM roles to retrieve those credentials for you. So the typical workflow will be that a DBA sets password for application still, stores it in the Secret Manager, and then sets the rotation on. So the first time he might know what the ID and password he set, and after that it will be automatically rotated and nobody knows that ID and password. Now your DevOps guy, he goes there and designs at the time of deployment, he grants IAM permission to the application to actually go and access Secret Manager service to be able to retrieve that password. The Secret Manager service can actually rotate that password and has the facility that it always issues you the latest version of that ID and password. So in this case, if you think about that architecture, nobody actually has to care about what the password was because it is being rotated behind the scenes for you. Nobody has to care about whether they will get the latest version of password or not because Secret Manager is already giving you the latest password, and based on IAM, you can set permissions on how to actually retrieve that directly to the application without the DevOps guy or the DBA having to know about it. So a very powerful technique. Just keep that in mind when you are building your POCs because it's not just about your databases. You have to work with your applications to lay out in a secure way, right? Now just summing up our security discussion, the last thing I want to discuss in security chapter is the database activity stream. It was a much asked topic. People who are in the governance space raised this question that we are doing auditing, but the audit logs are still getting stored in the database, and the DBA has access to the audit logs. So what do we do about the insider threat, which is like the biggest threat sometimes? So we came out with database activity stream, which out of the box gives you a way to stream out your changes using Amazon Kinesis stream out to either CloudWatch consumer, or it integrates with third party. Right now we support IBM Guardium and McAfee's Impreva. So you can consume those changes there and build reports and dashboards based on that and alerting mechanisms based on that. So if you are in that space, keep that in mind that you can use that to your advantage apart from the regular auditing features that we offer you. Next thing, and another important one with your POCs and operations is about backup, restore, and snapshots and how they work and how you would use them in your operational procedures, right? So let's revisit how Aurora backups work first. The way Aurora backups work is they are continuous in fashion. We are continuously taking snapshots of the segments and streaming it to S3. Behind the scenes, when you run the restore, there are these hundreds of storage nodes which power the volume. They actually work in parallel to consume those changes from S3 and apply recovery in a fast manner because we do not have to go through the wall log files to do the recovery. And there is a hot log segment attached there. So recovery in a nutshell is really very fast for you, and you don't really have to think about how the backup window should be configured, because ideally there is no backup window in Amazon Aurora, and it's a continuous backup which is happening. We like to call it continuous backup and continuous recovery scenario, right? Now, the reason for that is the storage is actually transaction aware, and we continuously replay the log records. That's why it's super fast in fashion. So from an operational standpoint, what does it mean? The first thing which people ask me is that I'm coming from my enterprise background. This is how my backup policy used to look like. So what do I do when I'm designing my operational procedures on Amazon Aurora? You just need to discard that, right? Because there is no backup window. There's no concept of full and incremental and so on. You don't need to worry about this. What you need to just think about is how do you wisely choose a retention window, and that's mostly about it, right? So what are the things which you really have to do? Is there nothing that you have to do with backups and restores? Well, the only thing you have to do is keep in mind that follow the industry best practices with backup and restore scenarios, right? So we take care of most of the things for you. The industry best practices are the importance of logical backup. We are doing it in a managed environment. Does not mean that we are telling you not to discard your logical backups. Logical backups have always been a way to actually supplement your physical storage-based backups, whatever tools you use, or database backups. Or you might be in a need where you are working with tables and schema and database level, and might want to supplement your backup strategy with logical backups. Now, one of the way to take logical backups is with pgdump, and another advantage which pgdump gives you is it goes and reads that data. So you can detect a lot of problems with your residing data as well with logical backups. Very important to keep that in mind. Another good industry practice is choose a retention wisely. Now we give you up to 35 days, but out of the box, we give you a default 7 days retention window. A lot of time people figure out after 2 weeks that there was a problem going on. So you have to really think about at least choose like 3 weeks of retention window for your backups, right? Look at your how the pricing works and what best works with you, and choose a wise retention policy which works well with your or gels well with your operational requirements. Another thing to keep in mind is that know that there is an advantage of taking manual snapshots as well. People like taking manual snapshots when they're just rolling out a major change, but apart from that, keep in mind that you can use manual snapshots to send it cross-region for your DR strategy. For example, and manual snapshots can be retained for a longer amount of time. Even if you destroy your cluster for some reason, all the automated snapshots will go away with that, but manual snapshot will just be retained. So you can bake your manual snapshot in some kind of operational policy to take best advantage of that still, right? Another thing you have to I highly recommend is always practice the time to restore. How much time does it take to restore on different size of servers? And what does it really mean? A lot of people realize when they're restoring that when we restore, we give you an option to choose parameter group, choose VPCs, and so on. They end up being in a different VPC, and then they realize that after the restore, I'm not able to connect to that server, or my database parameters have changed. They don't behave like primary. So even though we do that for you in a managed environment, there are things from operations standpoint which I highly recommend you need to test around, especially when you are doing these POCs and building operational runbooks. Just test around those things and build your operations accordingly as per the operations or industry best practices, right? Now, another thing is with auto vacuuming and optimizer stats. Now, we made some changes to vacuuming. Now, let's talk about vacuuming a little bit. It's a garbage collection process in PostgreSQL. The way MVCC works in PostgreSQL is that there are multiple row versions, and if you just leave it for a while, you will see that it leads to bloat issues. So in PostgreSQL, you have to actually rely on vacuuming process to clean up those dead row versions, right? If you leave it for a while, this is how it looks like. The red line is the normal TPS, expected TPS, but if there's a bloat, you can see that the TPS rate goes down when the bloat actually starts coming up. It's very important to do vacuuming in PostgreSQL, right? Another thing why you do vacuuming in PostgreSQL is about the transaction ID wraparound. So there's only 2 billion in-flight unvacuumed transactions that can be there, so just a concept to keep in mind. But when we were designing Amazon Aurora, since the storage was designed and was log-based, we had to do vacuuming enhancement, otherwise vacuuming would just not catch up with the fast changes which we are doing on Amazon Aurora with high throughput system and so on, right? So let's compare how the Aurora PostgreSQL works with respect to vacuuming. Now in PostgreSQL, there's a concept of visibility and frozen map. So PostgreSQL just, instead of doing the full scan and finding out row version, it just goes and finds using the visibility maps, which are the rows that need to be cleaned up, right? And it uses a prefetch, and what it does is when it finds the row, it reads another 32 blocks and does a prefetch. Now, we do not have a concept of prefetch or file system cache in Aurora PostgreSQL. So the thing we did is we came out with an intelligent vacuum prefetch, and we just find those addresses and store it in one IO block of 256 KB batch size and just do it intelligently for you. Net, since we do not have to do checkpointing and full page write, and since we are doing this prefetch thing, the vacuuming in PostgreSQL works 50% better, right? So that's the out-of-the-box configuration for you. But if you think about operations and what do you need to do with it, right? Is that I recommend two main things when you're working with vacuuming. One thing is work with the auto vacuum logging level parameter, very handy. By default, we are not logging auto vacuuming in PostgreSQL log file. It really helps you save hours of operations thing because if there is a conflicting log and auto vacuuming is getting skipped from a table, you can quickly go to the log file and identify that if you have enabled it. Another thing is we have a CloudWatch matrix on the transaction ID wraparound, which I just discussed. You should go ahead and build monitoring on top of it to alert you at a suitable time. So for example, in this case, I built a alerting system which will alert you at 1 billion transaction, and this is how the alert would look like. There's a blog post out there which explains it in great detail, but highly recommended if you're working with vacuuming, just keep these two things in mind. Next, let's just discuss about the monitoring and alarming system. Most important topic, if you're working with operation, you need to know what are the tools available. Right now we offer CloudWatch log, performance insight, enhanced monitoring, database log file and events, and you can use your own third-party tools to actually monitor Amazon Aurora. So CloudWatch log has been out there for a while and offers you a lot of advantages. We collect metrics like CPU usage and IO and so on. But if somebody asks me like what are 4 main things you would watch out for in PostgreSQL, my top 4 things would be transaction ID wraparound, which I just discussed with you. The free local storage, which I just told you, is used for the log and the temp file, so build alarms on top of it. Memory and swap is again something which I cannot ignore when working with any RDBMS, is really of great advantage and highly recommended that you watch those metrics. And one of my personal favorite is the DB load, which in CloudWatch is getting populated from the performance insight. What it does is a neat way to actually tell you that what your active sessions are doing at a given time. Most of the time when you will run into performance issue, you will see that the SQL is performing slowly, and what ends up happening is that the sessions start piling up. So it's a good early indicator of those kind of problems, which you can identify that your CPU is shooting up on a lot of other problems by just building an alarm on what's the average active sessions which are getting built up there. So important to keep that in mind. Now you can publish this CloudWatch in CloudWatch logs and build metrics on top of it. So as a DBA, you might want to actually, when I was working as a DBA, I used to do like a grep command and find out like where my logs are having the most entries and what's the pattern that is being there. You can do that with CloudWatch logs, very handy feature. Publish the PostgreSQL in the CloudWatch log files. Another important feature is that you can use the CloudWatch log insights actually. Now in this example, it shows that bar, if you can see, is the point where there are a lot of logs which just showed up there, right? So there, if there's a connection blast which came out there, you can actually go to the insights and see that what's the point in time where you need to focus more on that, right? Another thing is you can put a filtering pattern in there and actually find out where you need to focus based on that. Another tool which is available to you is the enhanced monitoring. If there's one thing which I like about enhanced monitoring is that it gives you a very granular thing, like you can go up to like 1 second interval to find more about your various OS metrics. Another thing which I like is that it gives you a good dump of the background processes. So if there is a time when you are working with your performance issues and you want to work with and say like what's my select query doing and which session is actually consuming more CPU, you can take advantage of enhanced monitoring. Highly recommended that you actually turn it at least at 5 second granular interval or even more aggressive. Comes very handy in your operations, right? Another thing a lot of people just ignore is that there are events, and there are a lot of these events which we publish that. You can build alerting on top of that. Your database goes down, goes up, failover happens, your CloudWatch metrics can alert you based on that. If your parameter is being changed and you're working in a global environment and you want to make a tight control, the first thing I used to come up in the morning, and especially on the Monday morning, was to check like what are the changes which has happened in Saturday, Sunday. I might have missed an email or something, right? Now this gives you a centralized way to actually see what are the changes which are showing up in the events, so you can have a close control over your operations monitoring as well. Finally, Performance Insight. We gave you a tool, and it came out with Aurora PostgreSQL quite a while back. It gives you a window inside your database to actually see what are the average active sessions doing right now, what is happening right now inside my database, right? So you can hook on and see the current activity which is going on, look at the active sessions and find out what your SQLs are doing, what are the top wait events, and what are the explains plans related to that. Comes as very handy, and I'll show you that in the performance monitoring example. So for example, you are using a Performance Insight tool and you identify that there was a SQL which started behaving bad. Commonly what happens is that there might be a plan flip, right? So the statistics might have changed overnight and your SQL performance just goes bad because the plans have changed. So that's where Performance Insights come very handy. But another thing which we released was query plan management, because people asked about how we can make sure that we can get a stable performance, right? So with query plan management, what you can do is lean more towards predictable performance. So if your system is behaving at a baseline performance, say you did a POC and you worked in a lab environment and you get a certain performance and you want to make sure that that performance is something which you want in production. You don't want these plan flips, or you do not want surprises in your production. You can use query plan management to capture all these statements which are performing at a baseline, and you can set a baseline and say, hey, I like this plan and I want this stable performance. So no matter what, even if the statistics change, I do not want my plans to do that unless I manually approve that. So you can create a baseline, and your plans will always be whatever are defined in the baselines without relying on the change statistics, right? So it gives you a very predictable performance. So if there is a bad plan which comes, it won't now be affected or affecting the plan which is in memory, because you already have a baseline. But what if there is a new plan which is better and can improve your performance? So we give you a way to actually manually approve that plan, and you can evolve the better plan and put that in the baseline by comparing it if it's better or not, and can actually start using that baseline, right? So what are a few other cases? Just summing up here are three main cases that you can use this for predictable performance. One thing is that people say I have a third-party application. Now I do not have the control. How do I actually use that? Third-party application controls my SQL queries. I cannot do that. But if I put a hint in that SQL, it works better, but I cannot go back in my third-party application and put the hint there, right? So we give you a way with query plan management to actually integrate with PG hint plan so that you can actually use that effectively. So without changing your SQL query in your third-party application, you can actually use PG hint plan to use the hinted plan to be used in your baseline as well. Another thing you can think of is that in your dev and lab environment, you might actually find a good plan, and you might find a need that you want to just take that plan and put it in your production environment and say, hey, use my dev plan because it's a better plan, and use it in production. So you can pretty much export the plan out and put it in production and use that. Another thing you can think is about the major version upgrades, right? A lot of time when we go from version 10 to 11 and so on, we see that the plan regression happens, although the new version is supposed to behave in a better way, but there are plan regressions which might happen. So you might use query plan management in that case to actually fix the baseline, and after the major version upgrade, you can use that baseline to actually get a more predictable performance. And over time, you might realize that there are better plans, and you may manually want to actually use that to your advantage. All right, sorry I have to rush in the last bit because I was running out of time, but I'll be available on the side to take more questions if there are any questions with this session. I hope you really find useful the information which I shared with you. It's really hard to squeeze in operations topic in 1 hour. There were 10 different topics, but I hope you can take bits and pieces of these things and be more successful in your operations. Don't forget to please give the survey. Thank you.